I've released all the videos except for 1 week videos on NP completeness. So that's where we are. So hope you got a chance to look at the videos on dynamic programming, greedy, and graphs. So there are 2 assignments with you. Yeah, so I'll be up for any questions or comments you have, anything. So this is, I mean, we are doing like a what they call flip classroom. So you have the videos and we use the live sessions for problem session or any questions or discussions. Last week we covered largely divide and conquer. So if you have any questions on dynamic programming, greedy, or anything else, we can handle now.
Sir, what do you suggest that if I start DP, so except Fibonacci, that is many books call it as a toy example. So apart from Fibonacci, from which problem we can start? I mean to say that, for example, knapsack, longest common subsequence, or Floyd-Warshall, or should I directly start matrix chain multiplication? So, or say that is a coin changing problem also. So, because we may go from easy to harder.
Yeah, I think it's a good question. Matrix chain multiplication is as a all the problems and the solutions have a lot of similarities. They all follow, in some sense, the solutions follow general template. So in that sense, they're all almost the same. But the matrix chain multiplication or optimum binary search tree problem may be somewhat artificial, or it takes a while to understand what the problem is. Whereas something like knapsack, at least the problem is easy to state and you can get on with it. So yes, starting at knapsack may be a good idea. Fibonacci I start, but Fibonacci is also not an optimization problem really. Fibonacci tells you the contrast between, very, very simple example where you can see the contrast between exponential and linear time, but it's not an optimization problem. So starting at knapsack, what else you said? Longest common subsequence.
And coin changing, Floyd-Warshall.
Coin changing, you can do greedy, right? So
DP also, for coin changing, DP also.
Yeah, wherever greedy works, DP also works. It's just that DP will be more less efficient. Floyd, yeah, I think knapsack may be a good idea.
Yeah. So even in that case also, what difficulty I face to formulate the equation. So once if I can make the or derive the equation, I think it is called also the recurrence equation. I think so. Then the problem become easy, but I face the difficulty to form this
recursive thing. Yeah.
Even though means the problem statement is clear to me. Every problem statement I can well understand, but from problem statement to derive this equation, this whatever recurrence equation or whatever the equation, that I face difficulty. So is there any means easy way to do that? I'll come to the matrix multiplication later.
Yeah, no, there is no easy way. It is just you gain by experience. And there is no magic thing. Yeah. So it's all about, in general, breaking the problem into small sub-problems, kind of a thing. But in each one, yeah. First, you have to start in terms of the choice function. What is it? What is the choice? So, for example, in knapsack, you have the first object. Should I put it in the knapsack or not? That's a choice. Once you put it, then there is a recursive sub-problem. If you don't put it, there is another recursive sub-problem. You pick the best of the lot. So it's about this choice, what you make. And no, it's no easy. I mean, yeah, you have to gain by experience, and sometimes even something like Floyd Warshall, it's not easy that formulated. You use the choice as what vertices the path can go through and not. So
Uh, uh, Even so that is why I'm asking. Suppose I have given a new problem. Uh, we found some in exercise, and how should I attack that? For example, I should try to find the optimal substructure and overlapping sub problem, this property.
no, as I said, there is no magic trick, but one thing that works generally is this choice function. What are the choices you are making? Break it up into different cases, and then once you fix that, you should find some recursive subproblems, and then you worry about you have this optimum substructure property exists or not, and take it from there.
Okay, now coming to the matrix chain multiplication.
Mhm.
So I understand the problem very well. No issue with the problem statement.
Mhm.
Uh, After that, um, say how to find this overlapping subproblem and optimal substructure property, and
Don't
this formula, how to derive the formula, that is not clear to me. That even if you can explain once more.
Yeah,
And
so don't get into the overlapping optimum substructure issues at all. They will come later. Think of the choices you have to make.
yeah,
Can you
so
break your problem, at least some choice, the first choice or the last choice, into some small number of cases? Once you bring that into that, you will see what are the different remaining subproblems you need to deal with, and you will have the recursive formulation. So, for example, if I have to do the matrix chain multiplication.
just I have a small thing to clear. For example, three matrix is given M1, M2, M3.
Mhm.
So what we can do, first we multiply M1 into M2,
Mhm.
then product of this by M3.
Right.
This is one way, and another way is M2 into M3 first,
Yeah.
then by M1. So
Right.
so we say that we can multiply three matrix in two way.
Right.
So my question is that, suppose if I do M1, M3 first, then M2 later.
No,
So
no, no. M1,
there is
M3.
problem of the matrix compatibility.
No, no, no. You can't do M1, M3 first.
Oh, that is not in chain.
Dimensions may mismatch, and
Oh, yes, yes, that is why. That is why.
so it has to be in that order.
Okay. Yeah. So, so can you please explain it
Yeah.
is
So
once
you
more
so
and with
you,
the help of an
you
example?
already said how to do it for 3. That's easy. So let's try for 4, right?
So, basic multiplication, number of multiplication, that is clear. That
Yeah, yeah, exactly. So you have M1, M2, M3, M4, right? So again, if you just like the way you enumerated for 3, if you enumerate how many for 4, one can do. There are a lot of choices, right? So you can say M1, M2, M3.
I think five choices are there.
Okay. So first compute this optimal way of doing this product M1, M2, M3 multiply by M4. Okay. Now you will ask, okay, how do I multiply this 3 things first? Well, that's the recursive formulation. That's an optimum way and so on. So we won't bother about it for now. Okay. Or I can do M1, M2 followed by M3, M4 and then multiply these two. Or I can, compute M2, M3, M4 and then multiply, right? I think that's all basically, except we did not specify how to do these 3 things. With that, again, you have more choices. Let's say we'll do it optimally. So in this case, for example, a natural choice would be, what is the last multiplication you want to do? So it's all about where do you put the brackets and so on. So what is the last multiplication you want to do is a choice. And for the last multiplication, we had these three choices, that I multiply M4 with the product, or I multiply this product with this product, or this product with M1. So you break your problem. I mean, I'll after doing this, I will throw in a completely new problem, something like a knapsack problem, and we can work it out. I just hope that I did not ask that. What is the problem I asked in the problem sheet for dynamic programming? Some subset sum or something.
And yes.
Yeah, okay. So then I'll throw in a completely new problem and let's see. It has a sort of knapsack-like flavor, and we'll see how to do it.
Yes.
Okay. So these are the three choices. Okay. So now the question is, how do I multiply? How do I compute in the first choice? How do I compute these three things? It's obvious that you have to do it optimally. This is the optimum substructure property, because, I mean, why do this product in a suboptimal way? You can always improve it. Similarly, how do I multiply this product? I have to do it optimally, and that's what the optimum substructure is. Once you break it up into three cases, the recursive formulation is clear, right? So then you just go and say, okay, number of ways of number of multiplications I need to compute T1 to 4 is one of the three things, T1 to 3 optimally, plus whatever you need. I haven't put the definitions. Or you compute T1 2 and you compute T3 4 plus whatever you need to multiply these two products. Or you compute T2 4 plus whatever some number, and you pick the min of the three. So here in this case, we made choice of what is the last multiplication I'm going to do. And the last multiplication gave us three choices. And then individual, I mean, once you do this, so let's do it for a larger example, right? So if you want to do M1, M2, M3, M4, M5, so you compute this. Okay, so so first you compute M1, M2, M3, M4 optimally. How do I compute it? I don't care. It's optimally. So that's a recursive thing. And then multiply by M5. Or you compute M1, M2, M3 optimally, and then you compute M4, M5. Or whatever, M1, M2, followed by M3, M4, M5. Or M1 into M2, M3, M4, M5.
Sir, as you have written first and last one, at a time we can multiply two matrices.
Yeah.
So you have written this 4 at a time means by 3 multiplication.
Whatever, optimally. So compute M1, M2, M3, M4 optimally, recursively. Whatever, take those 4 multiplications, whatever you need to multiply it optimally, recursively, complete that and then multiply with M5. That's what it means by. So I'm making the last choice of this product, let's call this some M14 as the final matrix of this, which I'm multiplying by M5. How do I multiply this? Well, that's recursively optimally. So we don't have to worry about it. That's the beauty of recursion. Once you say recursion will unravel and do everything. Except here, We are not doing it under recursively. We are doing it by storing the optimum solution in a table form. That's exactly the reason why you don't want to do recursive.
We can say as a recursive formula.
You can write a recursive formula, but you don't apply recursion. And this is where you have to come back to Fibonacci kind of an example. That even though there is a recursion, we compute and move up. So to compute the recursive formula, whatever it takes to compute this 3, whatever it takes to compute this 2, multiply. Whatever it takes similarly here. Okay, so if you have 6, there may be 3, 3, whatever. It's all about recursion. Okay, is there any other way? If you think of, how I do the in-between things, I do it optimally. This is where it says optimum substructure, because there's no point in doing it suboptimally, that product. I mean, how do I compute this product? Well, compute it optimally recursively. Again, at least for recurrence relation, we will say recursively, but we are not going to compute it recursively. We will have the table form to do it. Okay, so I mean, there's no magic trick. Only thing I would say is don't get bogged down by what are the overlapping subproblems, what are the optimum substructure. My suggestion is to focus on the choice. What are one choice? Of course, there are lots of exponential number of choices you have to do. That's why it's if you do it recursively, there are too many possibilities. But make one choice. After that, you will be able to do a recurrence, and then you will be in shape. Okay, so let's do one new examples. I mean, relatively simple one example, and then see how we do. And that is the set cover problem. Okay, you will get to it later when you do NP completeness and so on. But ignore all that. Let's look at the set cover problem. Okay, you have a universe. So also these choices, you have to do it very carefully, systematically. If you do it arbitrarily, again, you will be left with exponential problems and so on. So I have a family of subsets of U. Okay, so various subsets. So for example, maybe N is, let's say 6. F may be 1, 2, 3, 4, 1, 5, 6, 2, 3, 4, 1, 4, 5, 6, maybe 1, 2, 3, 4, 5, and so on. So there will be a bunch of subsets of the universe. And the question problem definition, what is the question is, find the smallest F prime, which is contained in F, that cover the universe. What does cover mean? That if you do a union of the sets in F prime, that must be your universe. Okay, is the problem definition clear? So in this example, I could pick 1, 2, 3, 4, 5, and maybe 1, 5, 6. These two sets together cover my entire universe, 1, 2, 5, 1 to 6. So given this huge family, I want to pick the smallest number of sets that will cover my entire universe. Okay, so that's a problem. Is it clear? Any questions?
Okay, clear.
Any questions on the problem definition? Anybody? Yeah. So let's write some parameters. Suppose my family size is, let's say, M, right? So there are N elements. So U has N elements. Family size has M elements. Okay. First of all, what would be a brute force algorithm? I always insist on some brute force algorithm for questions, right?
So check all the subsets
Yeah. So what subsets of what?
of F
Yeah.
and
Right.
union them and find which one matches.
Exactly. Very good. So try all possible subfamilies of F. F is a collection of sets. So you pick some subset and union them and see whether it covers it. So how much time will that take?
2 power n.
2 power?
N
No.
means here the number of subset is 2 power n.
Yeah. So 2 power m.
Okay.
Okay. Into something to check whether the union is maybe some m or something. Okay. Some small polynomial term, whatever it is, to check whether that union is f. So now I want to think of a dynamic programming algorithm. I want to improve this to something. Okay. So let's see how you will do it, right? So let's again, let me write down the problem. I have my universe, which is 1, 2, 3 up to n. And the family, let's call this f1, f2, dot, fn. Okay. I want to see if I can use some dynamic programming to solve this. Okay. So the first thing, as I said, is to think of the choice function I want to do, right? In a systematic fashion. Some arbitrary choice, you will get into problem. So, any ideas? I want to pick a collection of sets from capital F to cover my universe. So what sort of choice function can I use? Yeah, there are 2 power m choices, okay, roughly, because for every set, either I pick it or not. Every set in the family F, I pick it or not. So there are 2 power m choices. That's what we already saw for brute force algorithm. But I want to say that it can improve it if I use some sort of an optimum substructure property. Okay. So let's say, so yeah, anybody wants to toss some idea? What choice can I make? First, let's decide on the choice. And then let's think about, once I make the choice, what is our new problem? I'm sure one of you can come up with it. Some of you, several of you can come up with it.
New problem, you mean the subset sum problem?
Yeah. New version of new instance of a subset sum problem. It's not a new problem. It's the same problem. It's like, knapsack problem. You decided I'm going to take my first object into this knapsack or not. There are 2 choices. Either I put it in or don't put it in. Depending on that, I have a new instance of the same knapsack problem, which I recursively solve, right? So something similar. I even gave some big hint. So what choice should I want to do?
So whether I keep this subset or not.
Which subset?
Uh,
Let's do it systematically, right? From the family capital F.
yeah. So first subset.
Okay, good. That's it. End of the story. Once you bring into that, your problem is solved. Okay. So let's decide case 1. F1 is in the solution I'm looking at, and case 2 is F1 is not in my family which I'm looking for. Okay. I want to just walk you through and see that we'll be done. Just like, in the matrix multiplication, we said last choice, there are several choices to do the parenthesis. Once you do that, then you do some optimum substructure, you're done. So if F1 is in F prime, let's see what is our new problem now. What do I need to cover now? What subset do I need to cover? Using what? What am I left with? What is the new problem? I already picked F1 into the solution. So my original goal was to cover U, the entire U.
F minus F1.
U minus F1.
Sorry, U minus F1.
U minus F1 using what? What am I allowed to pick? Which sets? What are the sets I am allowed to pick?
From F2 to
Other
F.
than F1.
Exactly. Other than F1.
F1.
F2 to Fm. Okay. Now in this case, what is the new problem? What do I have to cover? I decided not to pick F1. So what am I left with? What do I have to cover? U, right? Because I haven't covered anything. I did not pick F1, so I have to cover U using same F2 to Fm. That's it. So I have made these two choices, pick F1 into the solution or F1 not in the solution. Now I have a new problem, which is new instance of the same problem, which is cover U minus F1 using F2 to Fm or cover U using F2 to Fm. Whichever is better, I pick. That's it. So now what is my recursive formulation? Let's write this as opt number of sets I need to cover using F1 to Fm. Okay, so let's write the English meaning of this. Number of sets needed to cover U using F1 to Fm. This is what it is. Okay. Now let's write a recursive formulation. This is equal to min of, because it's a minimization problem, right? Because I'm trying to find the minimum number of sets needed. So min of what? Can somebody tell me now? These two cases, right?
U minus F1 and
U minus F1
and U
and 2 to M, because my problem instance need two things, a universe and a family, comma U 2 to M. That's it. Once you write a recursive formulation, then you know what are the sub problems you need to commit. I mean, this optimum substructure is something I have already used, because once you decide F1, to pick F1, then the optimum way to, then for the remaining, you use optimum way to cover U minus F1 from 2 to N. Because why would you use any suboptimal way to do that? Okay, so the optimum substructure is used. So now you know what are the sub problems to compute. The sub problems would be opt of some subset S. This S would be contained in U and some I to M. Because any intermediate step, you will have, this set would be some arbitrary set and you're allowed some I to M. This is it. Now you compute this. That's it. So you made a choice. Should I include F1 or not? Then you got two cases and both cases had some recursive formulation. Then from the recursive formulation, you figure out what are the sub problems I need to compute. So the sub problem is that I want to cover some subset of the universe, not the entire universe. That's our final goal. But the intermediate goal is some subset of the universe I want to cover using some I to M. This is very important that here I am using I to M and not some subset of F. That will make it messy. Okay? So this is it. So now in general, this whole quantity would be equal to min of opt of S minus Fi, comma, I plus 1 to M, or cover the entire S using I plus 1 to M. That's it. And you know what are the subproblems? So the subproblem is some subset of the universe and some I to M. Now let's talk about what is the base case. What is the base case? What is where are you making some progress? What is decreasing? When I wanted to compute I to M, what I need are I plus 1M. Right? So the base case would be opt of any set S. What? What else? Where do I start? When I wanted I to M, ultimately I want this I is 1, because ultimately what you want is this. This is what we want. So to compute 1 to M, I need 2 to M pre-computed already. To compute 2 to M, I need 3 to M. I mean, whatever, for all subsets S, I compute how many sets I need to cover this set using F3 to Fm, F4 to Fm. So what would be the base case? I want to cover S using what? To cover S using I to M, I needed I plus 1 to M of some other sets pre-computed so that I can pull it up here. Now to get to I plus 1, I mean, all I'm allowed, so I plus 1 to M is the sets I'm allowed to use to cover my set. Set is arbitrary. So eventually, where do I start? What do I need? Opt S. Come on, somebody should be able to answer this. I've said it 3 times, so I'm going to tell you 4th time. To compute 1 to M, opt of S 1 to M, using this means I'm allowed to use F1, F2, F3, F2, Fm. You have some min quantities, but it needed 2 to M. That means using F2 to Fm, can I cover some subset, maybe the S or S minus F1. To compute 2 to M, I need 3 to M, 4 to M, and then 3 to M, I need 4. So that means I'm given restricted collection of sets to cover my universe. Ultimately, the base case would be what am I allowed to use to cover my set S. Come on, say something.
The last subset.
Exactly, Fm. Karthiban says M minus 1 to M. You take it even more, it will be just, you are allowed only set M. That's a base case. Okay. Now let's see, how do I compute the base case? Base case should not be a recursive formulation, right? Base case must be direct. That's a base case, you compute it and then you build it up to other cases. So what is by definition opt S M means what? I want to cover number of sets I need to cover S. It's a minimization problem, remember? Using the last set Fm. It's a minimization problem. So I want you to keep thinking about it. So what will be this value? When will it be 1? If that means to cover my set S, 1. Right now I have only one set, which is Fm anyway. When is Fm enough to cover S? If S is contained in Fm, right? So all I'm saying is here. So here's an example. I want to cover opt 1, 2, 3, 4 using my last set, which may be 1, 2, 3, 4, 7. In that case, you can say, yes, this one set is enough. Okay. But if I'm asking you to cover 1, 2, 3, 4, or the set is 4, 5, 6, then what should you put here? That means this FM is, so that's the case. If FM contains S, it will be 1. If FM is not enough to cover my set S, what should I put? It's a minimization problem. Okay, so this is not dynamic programming questions, right? This is just some mathematical formulation abstraction question. So I will put infinity otherwise. Okay, we'll come back and see what we have achieved at this point. But any questions? I want you to just observe what I'm doing, right? So
Infinity means that does not exist.
Exactly, this set cannot cover my set S. So how many? What is the minimum number of sets from my family I need to cover my universe? It's infinity. That means I can't even this. Even if you pick all the sets, I'm not able to cover my universe. Okay, so infinity is sort of saying infeasible. Okay, so now let's just go back and see what. So what I'm saying is I want to cover my set S. Now my family contains F1, F2, up to Fn. Okay, so before I think of covering with all the sets, first I want to say, can I cover it with just Fm? Then can I cover it with, or what is the minimum number of sets I need if I'm allowed to give? Remember, this is what happens in Floyd-Warshall shortest path algorithm, if you know it well enough. I want to go from X to Y, but you are restricted about what intermediate vertices you are allowed. And we will gradually extend it because it's just going to build up in the bottom-up fashion. So similarly, I want to cover my set S, but I give you only these two sets. How many? 3 sets, 4 sets, and then finally I give you this entire set. To start with, I'm giving you only Fm. So then I have one of these two answers. Okay, if Fm covers S, I will say one set is enough. Otherwise, I'm going to say infinity. Now, no amount of sets is enough from what you've given me. Okay, so now let's just go and say, and then now let's go back and use this formula. Okay, so the base case for any set S, opt S M equal to 1 if S is contained in Fm and infinity otherwise. Now let's go to the next case, opt S. Suppose I give you M minus 1 and M. Okay. Now it's the minimization of two quantities. Either I pick M minus 1 or not. Oh, sorry, I missed something before. There is this one little thing. In this, let's see if somebody can correct me on this. How many sets I need to cover S using I to M? I said either I pick Fi, then cover S minus Fi using I plus 1 to M, or I don't pick Fi and cover S using I plus 1 to M. Okay, I missed something here. I don't know whether anybody noticed. How many sets do I need? Or let's even go back here. So if F1 is in my solution, I cover U minus F1 using F2 to Fm. Whatever the optimum number is, remember we need to add a +1. Here in this case 2, you don't need to add a +1. Do you see why? In case 1, remember our definition is number of sets I need to cover my universe U. So either I pick F1. In that case, whatever you need to cover U minus F1 from F2 to Fm, take that number, and I'm saying you need to add +1. Why? In the second case, I don't need to add +1. So what I want to say is that +1. I'm going to wait here and see. I have to add +1. Why?
So I need the count of number of subsets.
I want to find, there is a measure, I'm measuring something. Okay. The measurement is how many sets I need to cover my universe if I am allowed F1 to Fm. So I make the choice. Suppose I include F1 into my solution. Okay. Then whatever the number of sets you need to cover U minus F1 using F2 to Fm, take that number and add +1. Why +1? To account for F1.
Because I have already taken
F1, right?
1.
Because that's a 1. I have to count for it. That's why. Whereas in the second case, I don't include F1. I don't need to do +1. Okay. So let me again now the general case. I mean, we need to analyze and see at the end of it, remember what was our benchmark algorithm complexity? We already saw a brute force algorithm. What was the brute force algorithm complexity?
2 power m into m.
Yeah, where are others? Nobody is
2
speaking.
power.
You're all,
Sorry, m into 2 power m, sir.
yeah, you're all switched off or what? 2 power m times
2 power m
something.
subsets
Yeah.
into number of operations for m. For
Exactly.
union operation.
Exactly, right? I'm going to now improve that. Let's keep that in mind. So that is one algorithm we know. Now I am trying to design dynamic programming by making these choices and recursive formulation. So my aim is to drill that template of dynamic programming, which is make a choice, then you have a recursive subproblem based on overlapping substructure and so on. So we made the choice of including F1 and not including F1. And that gave us the recursive formulation. So now the base case is this. Now what is opt S m minus 1 m? Either I pick F m minus 1. So it's opt S minus F m minus 1 using m, or don't include Fm minus 1. So that means cover the entire S using this. Now these two quantities in the brackets we have already computed, because we have already computed opt Sm for every S. So we know these two quantities. So based on that, I can compute opt Sm minus 1. Is that clear? First of all, let's stop here and see whether you understand this. So base case, let's try for every subset using only FM. Can I cover it or not? That's done. Now I move on. I compute the next step. I'm allowing FM minus 1 and FM. I want to come see how much can I cover. And that I use this recursive formulation. Either I pick FM minus 1 or I don't. And based on that, I have some recursive formulation. So now I compute opt S M minus 2 comma M. Again, I have this min of these two quantities, but those two quantities are already computed because they're all going to be some subset using the interval m minus 1 to m. So I can gradually go down like this. Eventually, I will have opt of S using entire 1 to m for all S. And so we also know opt of U 1 to m. That's what I wanted to find. Okay, so we made the choice function. Should I include the first set or not? That immediately, instead of doing brute force, we can say, well, we can compute the optimum to cover the remaining. There are two choices, compute them and pick the one which is better. So you have a recursive formulation. And from the recursive formulation, you should figure out what is the sub problem I want to compute. I want to cover some subset now using some I to M. So keep doing it from starting from the base case, which is simply M, and then you build it up, zoom in. Eventually, you will get opt S 1 to M, and so you will get your cover the entire original universe using 1 to M. Okay, this is how you are doing this table lookup, and everything starts from making your first choice. In the case of matrix multiplication, the choice was what is the last multiplication I'm doing. In the case of shortest path, all pair shortest path, you will say, what is the extra vertex I want to use. Either I use 1 to k or 1 to k minus 1. From there, you will move to 1 to k. So here we make the choice, should I include the first set or not? So different problems have this, make some choices, bunch of cases, write a recursive formulation, figure out what is the sub problem I need to compute, and then where do I start. From the recursive sub formulation, you should be able to figure out where do I start, because in our cases, I to m required I plus 1 to m on the right hand side. So I needed I plus 1 to m first. I plus 1 to m required I plus 2 to m. Eventually, I needed some m, and so that is a base case, and move from there. Now let's understand how much time have I computed, have I spent, right? So again, I think in my videos, I've given some quick and dirty method of computing the running time. Anybody? How do I compute the overall running time? So you probably haven't seen the videos yet. Maybe I should give time for you to look at the videos. How do you compute the overall runtime for a dynamic programming algorithm? First, compute number of sub problems we are computing. So what are the sub problems we are computing? What are the sub problems are we computing? We did, no? Eventually, here, our algorithm starts here. What are the sub problems that we compute?
n minus 1.
M minus 1. We have to do this for every S contained in U. So for every, because when I come here in the second case, I don't know what subset I'm going to land up. So I should have computed for every subset using M in my subproblems. So I'm doing this for every subset. So how many subsets of one U are there?
M.
Or 2 power n. How many subsets of my universe are there? I'm computing for every subset.
2 to the power m into m.
2 to the power n into m, because so essentially, I mean, my subproblems are opt S I to m. Okay, so how many choices are here for S? This is 2 power n, and here it is the I, which is m. So 2 power n into m choices are there. That is the number of subproblems I compute. And then for each subproblem, how much time does it take to compute that? The formula is here. To compute opt of S, some S and some interval, it is minimum of 1 plus opt of some other S and some bigger and smaller interval, which I've already computed and stored, and opt of this. So how much time does this take for each subproblem? Okay, so you have to go and look at my videos again. I don't think people have seen the videos of dynamic programming yet. Nobody can say this? How much time does it take to compute opt S I to M, or whatever I have written here? I mean, I have the entire formula here. Here it is, right? Opt S I to M is min of something, I plus 1 to M. So suppose you have already computed for I plus 1 to M for every subset S. I have already computed and stored. Then how much time will it take for this? I should add a plus 1. I mean, this is really 8th standard question, really not a dynamic programming question. Just listen to my English statement and then answer. If I have already computed opt of S, comma, I plus 1 to M for every S, I've already computed and stored. We are not even going to count time for that. I've done that. Now, using this formula, if I want to compute opt of S, I to M, how much time would it take?
Constant time.
Constant time, yes, exactly. It's just a min of two quantities. It is a minimum of two quantities which are already stored. Table lookup. I collect them and then do it. That's the beauty of dynamic programming, right? You're filling up some table. You already have computed something, and it's just a min of two quantities. In the case of Floyd-Warshall algorithm, it may be min of some n quantity, so it will take n time. Here it's min of two quantities, so constant time. So to conclude, I have number of subproblems is order 2 power n into m, constant time for each. So overall, the running time here for set cover using dynamic programming is some order 2 power n into m, which is an improvement from 2 power m into polynomial. M is much larger than n. So this is simply 2 power n into n. Okay, so more than the specific problem, my goal was to illustrate the templates of dynamic programming. Make some choice, small number of choices. Like we said, case 1, case 2. This is what I would do. If you want a new problem, make cases. It's not easy. I'm not saying there is some magic trick. Once you write down the cases, then you see that for each of them, using optimum substructure property, you have a new instance of the original problem. So you can write a recurrence. Once you write a recurrence, you can figure out what are the sub-problems you want to compute. And once you figure out the sub-problems, you can figure out the order in which you need to compute. That tells you the base case, and then you proceed from there. Okay, so that's the thing about dynamic programming, but let's spend maybe another 5-10 minutes on any general questions, if not about these examples.
Yes, sir, I have some more questions.
Yeah, go ahead. We already spent 1 hour, so I take 5-10 minutes more. Yes. I have another meeting to go to actually.
Greedy and DP both are used for the optimization problem, and sometimes what happens that this overlapping substructure property is present in both the paradigm, and sometimes what happens that we get confused. Suppose I have given a new problem, optimization problem, so we get confused to choose among greedy and DP. So what are the guidelines?
So DP is safer. DP is a safer approach because it explores sort of all choices. Whereas greedy makes greedy choice, which may or may not work most of the time.
So even for example, for fractional knapsack.
Yeah.
So greedy is the better choice.
The DP is always a better choice.
For fractional knapsack, greedy is the better choice.
Greedy works. See, greedy is more efficient, but it may or may not work in general. You're talking about a new problem, right? So for fractional of knapsack, if you use greedy, you have to prove that greedy gives the optimum solution. That is an added extra necessary thing when you apply greedy algorithm, whether it's fractional knapsack or Kruskal's minimum spanning tree, Prim's spanning tree, you need to prove that your greedy choices are correct. Okay, so DP is safer because you are going to explore all the choices, but greedy is more efficient. Why? Because greedy avoids a lot of choices, and so greedy, if it works, is more efficient.
Okay, so for the TSP, there is also dynamic programming version. So is it good to discuss TSP in DP, or what best paradigm we should discuss for the TSP for this course? I'm not talking about some approximation or this type of algorithm.
TSP, DP is certainly a good thing to try. In fact, I mean, you do DP. I know, in fact, some of the curriculum has TSP, DP, but you need to understand the running. See, we did the set cover. Set cover is also an exponential. It's important that you do this. I did DP, but you have to convey this story that with DP, what did we achieve is the story that needs to be told. Similarly, in DP for TSP, can you tell me what do you achieve?
I think from n into 2 power n to 2 power n.
No. No. You still do, it will take 2 power n into some n square or n cubed. What is the brute force algorithm for TSP? How much time?
N factorial.
Yes. So it is an improvement from n factorial to 2 power n. That is a message you have to convey. It's not enough to do DP. You have to do DP to illustrate DP, but to convey at the end of it that if you don't use DP, the brute force algorithm is worse. N factorial is much worse than 2 power n into n square. So that needs to be conveyed.
So this TSP is very interesting problem because all greedy, DP, backtracking, and branch and bound. All
Correct.
four are, yeah. So which one you suggest that?
Oh, greedy does not work. In fact, TSP, you have to do greedy to illustrate that greedy does not give you optimum. What, I don't know what is greedy algorithm for TSP. What is the greedy algorithm?
That exactly I can remember, but
First of all, there is no one definition of a greedy algorithm, because even for minimum spanning tree there is Prim's algorithm, there is Kruskal's algorithm. Both are somewhat different algorithms. So greedy is something you make some greedy choice, but there is no unique thing. Greedy choice can also be one of many things you will make. So in my opinion, if you do greedy, it is two things need to be emphasized. Greedy does not give you optimum solution. In fact, that's why I have an entire problem sheet. If you see, all the questions I asked are give an example where greedy does not give you optimum solution. So to know that greedy may not work all the time, proof of correctness is important for greedy algorithms particularly. In fact, proof of correctness is important for all the algorithms anyway, but for most other algorithms, most other algorithmic techniques, the proof of correctness is relatively easy. And if you want to show merge sort actually gives you a sorted list, that's not very hard to prove because each one is sorted and merging does the correct job. So you just need to prove correctness of the merging algorithm, and that's not very hard. Whereas to show that Prim's minimum spanning tree algorithm actually produces minimum spanning tree at the end, that's not easy. So to summarize DP and greedy, DP is always safer, but more expensive, more inefficient. Greedy is more efficient, but greedy requires proof of correctness, and greedy may not work all the time. So if you want to do TSP, do greedy and show that here is an algorithm which does not give you optimum, and, some greedy choice. And then you do DP and say that it improves from n factorial to 2 power n. Without that story, doing DP is not good enough.
what about branch and bound for TSP?
Branch and bound is okay. Yeah, it's no longer a fashionable algorithm thing. Modern books don't talk about them, but it's okay. It is again a brute force exponential time algorithm, except you are, keeping track of some more expensive solutions, so you don't follow through that route at all. Yeah. Okay, so dynamic programming is very powerful. A lot of, in fact, Olympiad problems and all cover dynamic programming, and there's no magic trick. But I have, like master theorem for divide and conquer, I've given you some master template. Hopefully, it's useful. Yeah. Okay. Any other questions? Otherwise, we'll. Okay. Thank you. I hope I've given a long gap for the problem sheet, so I hope many of you have already solved the problems. Look forward to seeing you next week then. Yeah.
Sir, actually, I was not well, so not able to submit the assignment third. So can I mail it?
This is the divide and conquer.
Yes, yes.
But we have already put the solution in the website. Yeah, okay, mail it to me. I mean, as a practice, we don't want to encourage this because then it opens up a lot of things. But mail it to me. I'll quickly check and tell you. Yeah.
Okay, thank you, sir.
Yeah. Okay. Thank you. Bye for now.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.